Hi, my name is Macy Lindblom.
I'm Sophia Cicero.
And I'm Renee Temple.
And our experiment was the effect of varying pH levels on the denaturation rate of protein. Although the title may seem a little bit complex, our experiment dealt with what many of you may know as ceviche, the popular fresh fish salsa, and had it on vacation or at the beach. Ceviche originated in Peru around 2,000 years ago, and since then has become a staple in the diet of many throughout the world. It's a common dish consisting of fish that has been cooked through the use of acids rather than the traditional method of heat, and is combined with various fresh ingredients such as tomatoes, onions, spices, and other seasonings. The fish in ceviche goes through a process called denaturation, which allows it to become safe for digestion, while retaining completely separate properties from a protein cooked through heat, however, a similar protein structure. During denaturation, the amino acids alter their interactions with the side chain of the protein and break the protein down into its most simple primary structure. Once in this primary structure, the protein begins to interact with other primary proteins, which then condense in a process known as coagulation. It is through this process in which it can be signified that denaturation has occurred because the protein becomes more dense and there's a clear color change. Ultimately, it's denaturation and its sub-processes that allow for the fish in ceviche to become safe for consumption and for the visual affirmation that a change has occurred.
Many professional chefs and home cooks make ceviche. The most effective pH level for the quickest denaturation rate is unknown when making ceviche. This experiment was performed specifically for that reason. In this experiment, the most effective pH level for the quickest and highest quality ceviche was found. Our research allowed us to form the hypothesis of, if protein is exposed to varying pH levels, then the protein exposed to stronger acidic or basic pH levels will denature at the highest rate. This means that the strongest acids and bases would cook or denature the protein the fastest.
First, we took all our shrimp and we soaked them in cold water to thaw them out. Then we halved all of them. Next, we took all 4 of our independent variables and we measured the pH of them. Vinegar turned out to be a pH of 2, lemon juice 3, orange juice 4, and green tea 5. Our research has showed that green tea would be more of a base with a pH of 10 or 12, but we measured it and it turned out to be more of neutral. We then put half a cup of each of these independent variables into a bowl. Then we also took 7 shrimp halves and put them into each bowl. We then checked on our shrimp 7 different times during 2 hours. When we checked on our shrimp, we took one out and we measured them using this denaturation scale. 0 being completely raw, and 4 being completely cooked, like this. Then we repeated this process 3 more times.
The overall results of our experiment were conclusive. These top graphs are each of our individual trials, and this bottom graph is an average of each of our trials. As you can see, vinegar and lemon juice denatured at the most similar rates, with orange juice shortly behind. In the beginning, the lemon juice was actually denaturing quicker than the vinegar, but around the 15-minute mark, that trend changes. They all reach full denaturation at 120 minutes, but the vinegar reaches full denaturation at 90 minutes, meaning that the vinegar denatured the protein the fastest. Also, the green tea had a steady denaturation rate, but could not reach a level of 3 even for the full duration of time.
In conclusion, our hypothesis was correct for the pieces we were able to conclude. It can be concluded that vinegar, which had the lowest pH of 2, is the most ideal for a quick denaturation time, as it reached a level of 4 first in every single trial. Although this would be the most ideal for a quick denaturation rate, lemon juice and orange juice would also work and may produce a slightly better taste for the actual ceviche dish and for use in the cooking industry. However, it would take a slightly longer time as they're not as strong. Our results for green tea were very inconclusive, however, because it was a neutral as opposed to the strong base it was originally thought to believe. Throughout all the trials, it never reached full denaturation and began to plateau around 90 minutes, allowing us to conclude that a neutral is not suitable for denaturing proteins and offering us no insight into the effects a strong base would have.
Although our hypothesis was proved correct,
There are many different variables that could have slightly altered our results. Our experiment had lots of room for human error. Since there were only 3 of us conducting the experiment, all the shrimp were taken out and measured at slightly different times. In a perfect world, all the shrimp would be taken out of the bowls and measured at the exact same time. Also, since there were only 3 of us, it would have been nice to have more people and have different perspectives of the colors of the denaturation scale.
Additionally, the most suitable and quantifiable method for gaining results would be a method called circular dichroism. However, this is only suitable for laboratory settings, and therefore we cannot use it in our homes. But in this method, light is polarized around a molecule, and depending on its level of activity, so for example, if it was a raw shrimp, light would be absorbed to a greater extent, and if it was a cooked shrimp, light would be absorbed less. And this would allow us to have precise numbers to actually show the change of denaturation.
Thank you for attending our virtual science fair. Bye!